up, guys? Mrs. Thompson here, and today we're going to cover standard enthalpy of formation. First, we need to know what that is. And so it says here, it is the energy change that occurs when 1 mole of a compound is formed. So that's forming a compound. The word compound is underlined here because you can only form compounds. You can't form elements, so we're talking about forming a compound. All right, so most of these values are negative. The reason for that is when you make bonds, there is a release of energy. And that's what's driving the making of those bonds. These are going to happen at standard conditions, and that's why you see this little symbol right here. Looks like a degree sign. Call it a knot. And so this happens at 25 degrees Celsius, slightly different than we were talking about gases, which was 0. So here it's 25. 1 atmosphere if you're dealing with gases, and 1 molar for aqueous solutions. Don't worry about that. Keep that in the back of your mind. We'll talk about aqueous solutions later. All right, so if you need a table, there's 2. There's 2 in your book, one on 510, another on page 921. All right, so something you need to know, like I said before, these are enthalpy of formation for compounds, so you cannot form elements. Therefore, all enthalpies of formations for elements are 0. So you'll see them in the equation, and you'll have to know that this is 0. So anytime you have an element in there, think of it as 0. It won't be in the table. Just think 0. This is for the most stable form of that element. So add that, please. And so sometimes the most stable form, as in the example, some of them are diatomics, like Brinkelhoff. All right. So here's an example of the enthalpy of formation for just water. Here you have hydrogen reacting with oxygen to produce 1 water. It's usually written in terms of the production of 1 mole of that substance. So that's why you see that half O2. Okay. And so you see that enthalpy of formation value, it's negative because making water is a release of energy. All right. So what we're going to do is we're actually going to find delta H of reaction, just like you did finding delta H of reaction using Hess's law, but here we're going to use delta H of formation values. Okay, and so what you'll do, and we'll treat it a little differently, is we'll use the coefficients from the balanced reaction, and we'll pay attention to when it's solid, liquid, gas, or aqueous, and we'll use this equation, slightly different. Okay, so it's more of an equation than it is Hess's law, but they are very much related in that we're adding up reactions to find an overall reaction. All right, so a couple symbols in here that might not be familiar. Sigma. Sigma is that little E-looking symbol. That just means sum up. If you're in calculus, maybe some other math classes, you might have seen that already. Okay, and then N, we know N. Actually, N is moles. We learned that in the gas unit. Okay, so what we're doing here is we're going to add up all of the energy for the products, and we're going to subtract the energy for the reactants. So it's kind of like when we find delta T and we take T final minus T initial. Here it's reaction final, which is products, and reaction initial, which is reactants. Okay, makes sense. We're looking for the overall change. All right, so here what we're going to do is we're going to do our first problem. So use the standard enthalpies of formation on 510. So grab your book. Here's what they look like. Let's see if I can zoom in. There's the table on 510. Okay, the way it's written is they're set up so that you are looking at forming the elements that it takes to form the compound. And so you have the enthalpy of formation values on the side, but all compounds are being formed. What you could do is you could manipulate all of these equations, or the ones that we need to make that equation, to get an overall reaction, just like we did for Hess's law. But enthalpy of formation, that little equation, products minus reactants, is a little bit easier in that we just need these numbers. We need to look at the coefficients in the balanced equation. So let's get this data on here. All right, so from the table, I'm looking that up. I see that ammonia has an enthalpy of formation of -46, right? And ammonia gas, make sure you're looking at gas. Sometimes you'll see different values for gas and for liquid, so be careful. NO2 has that value, 33, and then water in the liquid form is -286. Okay. What's missing in this table is oxygen, and this will always happen to you. You won't find it in the table because enthalpies of formations for elements are 0, and this is a free element. Low stable form is diatomic. All right, so we'll write that, free element. Okay, then we're just going to take that equation, delta H is equal to the sum of the products minus the sum of the reactants. Kind of simplified that, but it looks like this. So delta H is going to be 4 times, so remember I start with the product side. Be careful that you're not going in order of the reaction. It's products minus reactants. Okay, so it's 4 times the enthalpy of formation of NO2. So 4 times this one, plus, we have a coefficient of 6 here, 6 times the enthalpy of formation of H2O, minus, so there's all the products. We're going to add them together. That's why I'm putting them in brackets. You want to do that first. Okay, minus 4 times the enthalpy of formation of this reactant, plus 7 times the enthalpy of formation of that reactant. Okay, so we're going to do this in steps. And this is kind of like our general equation, products minus reactants, and I'm just stating what I'm going to be multiplying. All right, so that means, what do I have? I have 4 times 33 plus 6 times -286 minus 4 times -46 plus 7 times 0. Okay, take this piece by piece. That way you don't make any mistakes in your calculator or really use the heck out of those parentheses. So where I've used parentheses, use parentheses. I'm just going to go step by step and do some of the multiplication in the parentheses. All right, so that 4 times 33 would be 132 plus this times this here. So the reason you have to be really careful is because those negatives and positives, a mixture of all of them, are going to make a mess. And you'll get them wrong if you minus a positive, or I don't know, you'll make a mess. So please be careful with those. All right, so here we go. I've taken care of everything. Now I can just simplify, and that's equal to -1400. Now, of course, we have to worry about significant figures. So what do you do for this? I want you to round to places, since we're adding and subtracting here. So we're looking at places, and I want you to look at the givens. Where are those places at in the original table? So there are 0 places passed. So we're going to have 0 places passed, but we want to make the ones place significant because the ones place is significant in each one of those. So we're going to put a decimal at the end. And so our answer is -1400. Now, wait a minute, we need a unit. So in here, I left off the unit and the canceling of units because it gets really messy. For me, that's kind of hurtful because I love to see that the kilojoules cancel with the kilojoules per mole, or the moles cancel. I don't know. I usually like that to happen, but I'm going to let you get away with just multiplying the number times the value. Okay. So what are the units then? So if you look up these enthalpy values, they're actually in terms of kilojoules per mole. So make a note of that right here. Kilojoules per mole. And so when we multiply them, what we're saying is 4 moles times this many kilojoules per mole. The moles cancel, and you are left with kilojoules in your answer. So there's our unit, kilojoules. Okay, second example. This time we're going to use the table on page 921. So I'd like you to look for that table. Go ahead and find all of those values. Okay. All right, so what I'm hoping you noticed, we have values from the table for CH4 gas, and we have values for HCl. We do not have a value for chlorine. That's because it's a free element, so that's 0. And we do not have a value for CCl4 gas. We do have a value for CCl4 liquid, and yes, they are different. So this is unknown. That's a question mark. Okay, so what are we going to do with this problem? Well, what we do have here is we have a delta H of reaction. So this is negative 397 kilojoules. And so this is like a ending or answer that will make everything equal to, and then this will be our X value. Okay, so let's go ahead and plug that in. So delta H of reaction is going to be, this is our X part, 1 mole, because the coefficient is 1, okay, of the enthalpy of formation for CCl4. So this is what we're going to write here as our X. Okay, or you could write 1X, but I'd rather see it like this. Sorry. Okay, so then this is our first product plus this one. So it's going to be 4 times this. Okay. Then it's going to be minus the reactants. So 1 for CH4 and 4 for chlorine, which is just 4 times 0. Okay. Now in this example, notice I just started with the numbers here, and I didn't go through and do 1 times this HF for Cl2, this whatever. You don't have to do that. You can just start at this step. You're welcome. All right, so here we go. Negative 397 is the delta H of reaction. So I replaced that with this, with that. I'm going to leave the 1 mole of delta HF there. I combined these two terms, so by multiplying, that's the product that I got, minus, so this times this plus this, which is just 0, is negative 74.81. So be really careful, because if you notice here, you're going to subtract a negative, which will be like adding. So if you mess this up and your sign's up, then you'll come up with the wrong answer. All right, so combining those terms, great. First step, is there any other terms I can combine? Well, I can combine these two, because this is just being added. It's not being multiplied inside the parentheses. So I can just add these two. So that becomes negative 294.418. Okay, then what do I do? So hopefully your algebra skills are good. We're just going to move this over, right? So it's being subtracted. We'll add, and that becomes 102.582. Notice I haven't rounded yet. And then I'm just bringing this down. That's 1 mole of delta HF. So then how do we solve for delta HF? Now delta HF values are in terms of kilojoules per mole. That's why we went ahead and left a mole there. And so we'll divide by 1 mole. And so my answer will be this many kilojoules per mole. We're going to go back to significant figures. So let's look at places past the decimal for our givens here. So between here, that's 2 places past. Here, that's 3 places past. But here, there are no places past, so it's significant in the ones place. So my answer needs to be significant in the ones place. So right here, so the would be 103 kilojoules per mole. Okay, I want to draw your attention to the coefficient. In our example, it was a 1. Had this been any other number, like a 2, then when we took care of this part, it would be 2 moles HF, and then we would divide by 2 moles. Okay, so be careful when you have an example like this. Because the coefficient was 1, we just divided by 1 in the end and got negative 103 kilojoules per mole. All right, so we'll do a few practice problems like this, and hope to see you soon.